So as you saw previously, this system is generic enough that it doesn't care whether it takes user input curves or sort of procedurally generated curve inputs. All that matters is that you have primitives with a direction, or polylines with a direction. So I'm just going to go ahead and sort of bring out this little sort of bit here and put it off to one side for the minute. And let's just hook back in a regular old curve that's just going to be drawn in sort of the usual hand-drawn fashion. And this time we specifically care about the behavior of the path as it sort of travels up or down a slope. So I'm just going to go ahead and add a point in this valley here and another one at the top of this mountain. Okay, and we can see that it is already sort of taking a slightly, unusual path rather than the most direct line, but it doesn't really seem to care at all about the path that it takes up the slope, especially. If you remember, the costing at the moment only cares about sort of being attracted to these red regions. So let's just go ahead and just completely remove that actually for the time being. Let's go ahead and pull our old way of calculating costs off to the side there. And we're going to think about a more generic and sort of flexible approach to generating costs on our terrain. Of course, this is complaining because it's waiting to see a point cost attribute. So let's just create a little wrangle there and set f at cost to be equal to 1. So this just means there is some cost. Actually, let's just go with 0. There we go. So right now, the only thing that's being considered is the path sort of directly in the shortest sort of direction across the terrain. It'd be easier to see that if we look at the input curve as well. So there we go. You can see that it's just kind of going in pretty much a straight line. So yeah, we need to think about how do we start sort of considering this slope here. And one way in which we could do this is if we went ahead and sort of gave the actual slope a sort of a raw cost to just being on the slope. So let's go ahead and figure out that. So let's go and type float slope cost equals, and let's just say that the slope cost is equal to 1 for now. And then we'll set the f at cost to be equal to the slope cost. Okay, so we haven't actually given the slope a relative cost relative to anything else yet. And basically what we want to do is we just want to create a mask on this terrain according to the slope angle. And one way we can do that is we can use the dot product of the slope direction, or the slope normal, so you can see it's pointing outwards. So we can use the dot product of this angle, this normal, and the up vector, and that's going to give us a sort of black to white gradient, or a white to black gradient that's going to approach white the closer this angle here is to a tangent horizontal to the up vector. So let's just look at that in practice, and let's also set v at cd. So let's set color to be equal to the slope cost as well, and then let's set the slope cost, as we just talked about, to be equal to the dot product of the normal and some up vector. Of course, now we're going to get an error. And the error here is that, or the warning rather, although it is getting an error. So the error here is that we haven't initialized the up vector, but we also actually don't have a normal vector normal stored on our points. It's currently stored on the vertices. So first of all, let's create vector up. We'll set that to be equal to 0, 1, 0. That means up. And I'll just zoom out a little bit. Interestingly, it looks like it has automatically kind of done that conversion of the normal to a point. So maybe we can just live with this for the time being. Okay, so we're not really seeing the desired result yet. I think that we are getting it to some degree, but right now there's no really intensely steep slope angles, which is why it's not appearing to be very strong. So there is no lighting on the scene currently, and you can possibly make out that we're getting some shading, what appears to be shading anyway, on the steepest slope regions. And actually, if I turned off the rank, sorry, not if I turned off the rank, but if we just commented out that line there, we'll see that without that calculation, we lose all of that apparent relief. So we are getting something, but if we want to exaggerate that effect a little bit further, we can do a little power operation. So power open braces, then put a comma after that dot product, and then can put the power value there to 2, or maybe even to 4. So you can see that we're introducing more contrast. Of course, we want to make the cost be highest when it's on the slope as opposed to on the flat regions. And because we're actually approaching white on the flat regions and black on the slope, this is telling us that right now we've got the inverse of what we want. So I'm just going to do a 1 minus operation on the power, and we can now see that we're actually getting this white value on the slopes, which means that the cost is higher on the slopes, which is what we want. Okay, so we can't see that having any impact yet on the actual path finding that's happening. And if you remember, previously we had to use this attrib adjust float to multiply the cost value by a factor of 1,000 so that it would actually overpower the distance. So we're just going to do the same thing here. We could just type times 1,000, but then we have to come back inside and sort of change that value inside here every single time. And we can see that it's also actually modifying the color output. And actually, if we pay really close attention, we can see that this multiplication is taking effect before the 1 minus. So we're actually getting more regions in dark, and we want to do the opposite. And there we go. So yeah, we can just multiply it like so, but it's really kind of overpowering the preview. So let's go and just take that multiply, place it down here instead. So now the color isn't getting sort of affected by that, and we're able to change the value and modify the result. But let's also go and make this parameter. So let's go and call this parameter slope cost, just straightforwardly call that slope cost. Okay, and now we get this parameter that's been promoted. If we click this promote spare parameters, so it just automatically generates that there. And now we can just plug that directly in. Okay, so we're getting a slightly different result, but I would argue that it's interesting, but it's not really the effect I was looking for. So we can see that the pathfinding is kind of avoiding the slope. It's sort of taking the region that would involves being on the slope for the least amount of time, but it still is kind of like just going straight up. And in reality, if you were a person walking up this hill, or a car, as you might see, when you look at when you've been driving through the mountains, we actually tend to see that paths that are created by vehicles and humans as they go up tend to sort of crisscross their way up the slope here as they're going. And the reason why this isn't giving us that desired outcome is because right now there is a cost of being on the slope, but there's no cost that is considered, that would be considered for just going straight up it versus sort of like taking a shallower angle. So in order to properly consider this, we need to consider not just the cost of passing through the point, which is what we're currently doing. We actually need to consider the cost of traveling along the specific edges. Okay, so how can we do this? Well, if we go to the find shortest path node, and we just go and have a little look at the tooltip for the point cost attribute, or rather, the cost attribute on the output tab, which is actually probably in the wrong place and a little bit confusing. What we can see here is right at the bottom. Let's just go ahead and snip that so I can zoom in and sort of mouse over it and show you the bit that I'm particularly interested in. So the bit of this that is particularly interesting, even though it's a little bit hidden, is the fact that if there is an adjacency array attribute, this can optionally be an array attribute whose entries correspond with costs added to the directed edges specified by the adjacency attribute. All right, so interesting, but not quite what I actually really wanted to show you. But the thing that's important to know about this is that it essentially tells us that we can create, if we enabled here this adjacency array attribute, then we can create an attribute of neighbors, that is point neighbors for each point. So for point 2075 here, that neighbors attribute is going to hold the numbers of each of these points that it's connected to. Then what that's actually telling us is that the cost attribute can be treated also as an array attribute, which holds an array of costs, which corresponds to that array of neighbors. Okay, maybe a little bit confusing in theory, but in practice, it's actually quite simple. Where we currently have just a single float cost for every point, you can see that here we have our point and we have our costs. What we're going to do is we're going to create a costs as an array, which is going to store that cost of traveling to each of the adjacent points. Okay, so first of all, let's create an array of neighbors. I'm going to say I at neighbors, like so, and we want to get the neighbors on the current geometry of the current point. Okay, so I at neighbors equals neighbors of the current geometry at the current point. I think I just screwed that up because I didn't actually tell that to be an array. There we go. So let's just check out what we've got. On our points, we have that array of neighbors that I was telling you about. So if we go to 2075 or 20,075, I can't be bothered. You can see that we've got our points that are connected, the neighboring ones. So then what we can do is we can say for each int neighbor in the array neighbors. And again, I'm actually should be doing this as a variable and then promoting it to an attribute at the end. So let's do that. So we'll say at the very end, I at neighbors is equal to neighbors. And then this is going to be int neighbors, like so. And then we just need to complete our for loop. So then we can say I at neighbor in the array neighbors for each, let's do something, for each neighbor in the array neighbors. Then we're going to create an array of costs, so float costs, which corresponds with that neighbor array. And we can resize that to be the same length as the length of neighbors there. So that's just good practice to resize an array before you start doing things with it, because it's going to be more optimized. And then we're going to say costs at the current index. Okay, so we're going to say costs, this index of the costs array is going to be equal to a value. And for now, let's just say that it's equal to a uniform slope cost. We need to make sure that our costs array here is actually an array. So rather than just being a single cost value, it's actually an array, which is equal to costs. Okay, and now we're getting an error because we don't actually have this I value anywhere. Even though we're in a loop, we're not getting the current iteration of the loop. So what I can say is int I equals 0 just before that loop. Then I can say I plus plus, like so. Okay, so now every single time this loop runs, we're going to increment that I value, which means we get index 0, index 1, index 2, which means that we're getting the slope cost value for each neighbor, and we're putting that into an array of costs. So let's have a look once more at that spreadsheet. We can see our neighbors array, and we can see as well we have a costs array. So if we just expand that, you can see that if we have inside of the costs array, we have 1, 2, 3, 4, 5 entries. On the same line in the neighbors array, we also have 1, 2, 3, 4. I clicked the wrong line there. So 1, 2, 3, 4, 5 entries. 1, 2, 3, 4, 5 entries. But all the costs are the same. So we're not yet calculating a unique cost of traveling from one point to the next. Okay, so we have our slope cost, and that we're just going to leave that as it is because that's the cost of being on the slope. We need to create a new float called the ascent cost. And we're going to create another one as well called the descent cost. Ooh, descent cost, like so. Okay, and the difference between the slope cost and the ascent and the descent cost is that where the slope cost measures the cost, the sort of dot product of the normal of the surface, like so, relative to up, which is the same for each point here. What we're going to be getting this time is the dot product in the direction of traveling, so if we're going from this point here, which is point 20,146, going to this one, which is 90,955, we want to get the cost of, we want to get the dot product of this polyline, this little edge, and the up to give us that slope angle there. And then we're going to be able to see, are we actually traveling up or are we traveling down? Okay, so let's go and figure out how we calculate that. Unlike the slope cost, which can just be calculated on the point, this time we need to calculate the ascent cost inside of this loop because it's going to be different for every single neighbor. So we're going to say ascent cost, and we're going to say that we want the we need to get the kind of like direction of that edge. So let's go ahead and get the direction of that edge first, actually. So let's create a new vector called vector edge dir for edge direction. And we'll set vector edge direction to be equal to the current position. So that's v at p. And actually, let's just initialize a vector called current pos and set that to be v equal to p, because that's always going to be the same. So then we can say the edge direction equals current pos, something to do with the current pos, but also the target pos. So there we go, target pos, or even better, let's go with neighbor pos. So it's edge direction equals the neighbor pos minus the current pos. This is actually sort of a distance and a magnitude, or a direction and a magnitude. So we need to do something else to this later. But we're going to need to also set up our neighbor position. So let's say vector now neighbor pos, and vector neighbor pos we can just get by using this function point on the geometry 0, the positional attribute, and the point number is the current neighbor. So that's what this is, this neighbor here. So now we're getting the position of the neighbor. We're subtracting the current position from it to get the direction. And then what we can do is we can just say edge, or in fact, let's just do it on the same line. We can do a little normalize function there, neighbor pos minus current pos, which is going to give us just the direction without any length information, which is what we want. And finally, we can say float ascent cost equals, and then we're just going to do the same thing we did up here, which is going to be the 1 minus the dot product of the edge direction and the up vector. Okay, so this is just a little bit of inline kind of an inline expression there, just to give us something nice to work with. And then we want to give ourselves a sort of multiplying factor there. So we can say CHF, and we're just going to have a flat ascent cost for the whole, for the whole, everywhere across the terrain, the ascent cost is going to be the same. So that's why we can just multiply that there. Okay, we can set the ascent cost to be 50. And we're getting a little issue. So let's have a little look at what this warning is saying that the declaration is shadowing a previous declaration, and that's true because we've already declared the ascent cost up here. So I can go ahead and get rid of that. And another thing that we're doing is we're currently multiplying the slope cost by its sort of strength in here. So let's just take that back outside, just keep it next to the actual calculation. And then what we can do is we can add the ascent cost to the slope cost. There we go. I'm going to get rid of the color preview because the color preview no longer makes any sense because we don't have a single float value for each point anymore. And then let's go and put the slope cost down to 1 so that we're actually only looking at the ascent cost, and let's have a look at what we're getting. Let's play with different values for that. So, okay. So now we're seeing that we are still seeing like some kind of difference, but it's not altogether too clear the effect that this is having. It looks to be somewhat similar to the slope cost, but it is actually different. So let's just see what happens if we lower the ascent cost down and turn the slope cost up. Oh, it looks like it's giving us the exact same thing. So let's just do a little bit of debugging and see what the issue here is. I'm going to right click on the null, and then I'm going to go and have a look at the costs. Okay, so we can see that there is actually some difference in the values here, but it seems to be sort of fairly subtle differences at the moment as we like go through. I'm going to try and just mess with the input curve a little bit here because I actually really want the curve to be going all the way to the top of the mountain to see if we get slightly different behavior. And I think I did a pretty good job of kind of clicking the curve into the kind of correct location. Sort of at least, when I look at it from a top down, it does seem to be quite centered. So the reason why the pathfinding now is sort of going to the side of the hill and not all the way to the top is simply because it's going to look for the path to the point that's closest on the terrain pathfinding geometry, rather than the point sort of that's like projected down on a plane from the sort of in the vertical axis. So to ensure that that's what we're actually getting and that the point is snapping to where we want it to, it's going to put down a little ray node. Ooh. There we go. We don't need to ray after the costs, so we can do that before. And then I just need to make sure that that ray is actually projecting in a specified direction, which is directly up. There we go. But I also want it to snap down. So I'm going to give it a bias of minus 1,000 so that it's always going to, or minus like a really high number, so that it's always going to project it onto the terrain mesh. There we go. So now when we look at the find shortest path, we should see that it is going all the way from the bottom to the top. And what I would like to see, what I'll hopefully see now, is if we actually use a slope cost, we get a different result to if we used an ascent cost. Let's have a look. There we go. So as we increase the ascent cost to 1,000, we go, that is going to give us a different result to the slope cost. So the slope cost is just trying whatever it can do to avoid climbing up the sort of the steep parts of the slope. Whereas the ascent cost, if we drag that, make that even higher, is somewhat happier to go up the slope, but it should be kind of sort of wheeling from side to side more. So this is currently not what's happening. So I need to go in now and just sort of debug what's going on. I'm going to just disable the normalization for the moment. Ooh la la, that's a bit too much. Yeah, that's not what we want to be doing. So let's go ahead and put the normalize back on. Normalize is just ensuring that we get sort of a, a normalized vector. So the cost, the direction is always like a direction rather than a direction with any magnitude. And potentially it's because I don't actually want to have this 1 minus operation. So let's just try, let's try it without that. Okay, yeah. So it looks like that was what was messing things up. I was doing a 1 minus when I didn't need to, which means my logic here must have been slightly different to what I did before. Because now we're actually seeing the behavior that I kind of wanted to expose, which is as we increase the ascent cost, go and grab this, as we drag it up, you can see that what the pathfinding is going to try and do is while it's climbing up the slope, it's going to sort of pick more and more of these kind of loopy, sort of like zigzaggy kind of paths in order to avoid going up the steepest parts of the slope or in the most steep direction. All right, so we've got an ascent cost, but we're only halfway there. I'm just going to draw a few more curves just to illustrate my point. So if I was to draw one from the bottom up to the top here, we're going to see we get similar behavior. It starts sort of weave up the slope. But if I just undo that and then do it again, but in the other direction, we're going to see we get the exact same path, or pretty much. I may have clicked in slightly different places. So this is because we're currently considering only an ascent cost, which is sort of the cost of sort of being on a steep angle on one of these edges. It's not actually considering the direction that we're going on still. So that's the next thing that we're going to look at, is how do we make sure that we get a different result if we first click on top of the hill and then at the bottom, as opposed to if we click on the bottom of the hill and then to the top. And this is what's going to allow us to explore how we can do really interesting things like kind of pseudo river simulations.